Every single atom in your body right now, every breath you take, every beat of your heart holds a secret connection to the swirling galaxies millions of light years away. It sounds like science fiction, but this is the breathtaking reality of our universe. From the quantum flutter of particles smaller than we can fathom to the colossal dance of galaxies across the cosmos, there's an invisible web tying it all together. And today, we're going to unravel 30 of these cosmic threads, the hidden forces and phenomena that bind the smallest scales to the largest structures in existence. Think about the last time you looked up at the night sky, feeling that mix of awe and wonder. What if I told you that the stardust shimmering above isn't just distant and disconnected? It's part of the same grand story as the atoms in your hands. The laws governing the behavior of electrons orbiting an atom's nucleus are eerily similar to the forces shaping planets circling stars. Fractals repeat in the branching of neurons in your brain and the sprawling arms of spiral galaxies. Even time itself stretches and warps near black holes just as it slows down for particles moving at near light speed. These aren't coincidences, they're clues to a deeper unity, a cosmic symphony playing out on every scale. This journey isn't just about science, it's about rewriting how you see the universe and your place in it. We'll explore how quantum entanglement defies distance, linking particles instantaneously across space, and how dark matter's invisible scaffolding holds galaxies together like an unseen hand. You'll discover why the same mathematical patterns appear in the veins of a leaf and the distribution of galaxies, and how the birth of atoms in ancient stars echoes in the light reaching your eyes tonight. By the end, you won't just understand these connections, you'll feel them. So let's step beyond the ordinary and into a reality where everything, from the microscopic to the galactic, is part of one astonishing tapestry. The cosmos is whispering its secrets. Are you ready to listen, to understand how the universe stitches itself together from the smallest particles to the vastness of galaxies? We have to start where the rules of reality seem to bend the quantum realm. Here, particles don't just exist in one place at one time. An electron can be in multiple locations simultaneously, a phenomenon called superposition. It's as if a single note could resonate in every corner of a symphony hall at once, defying the logic of our everyday experience. Then there's entanglement, where two particles become so deeply linked that changing the state of one instantly affects the other, no matter how far apart they are. Imagine tossing a pair of dice in different galaxies, yet they always land on matching numbers. This isn't magic. It's the fabric of the cosmos at its most fundamental. The pioneers of quantum mechanics like Niels Bohr and Erwin Schrödinger wrestled with these bizarre truths. Bohr famously argued that reality isn't fixed until we observe it, while Schrödinger's thought experiment with a cat in a box exposed the paradox of particles existing in multiple states. But today's experiments go even further. Scientists have entangled particles across distances larger than cities, and quantum computers harness superposition to perform calculations that would take ordinary computers millennia. These aren't just laboratory curiosities, they're clues that the quantum world doesn't stay neatly confined to the microscopic. The same principles might shape the behavior of stars, the structure of black holes, even the way galaxies cluster together. Consider this, the uncertainty principle, which says we can't perfectly measure both a particle's position and momentum, mirrors the limits of what we can know about the universe itself. Black holes warp space and time so severely that they erase information, a cosmic echo of quantum unpredictability. And some theorists speculate that the quantum fluctuations in the early universe, tiny, random ripples inflated into the vast web of galaxies we see today. If that's true, then every star, every planet, even your own existence, traces back to the quantum fuzziness of an infant cosmos. The boundary between the infinitesimal and the infinite isn't just blurred, it might not exist at all. At the heart of both atoms and galaxies lies a hidden language of symmetry, a repeating pattern so precise it feels intentional. Take the humble hydrogen atom, where a single electron orbits its nucleus in a perfect spherical shell. Now zoom out to a spiral galaxy, where billions of stars swirl around a central core in eerily similar spirals. This isn't just visual poetry, it's physics revealing its deepest habits. The forces that shape an electron's path, gravity on the cosmic scale, electromagnetism on the atomic, express themselves through identical mathematical dances. One of the most mesmerizing examples is the golden ratio, a number found in everything from sunflower seed arrangements to the curl of a nautilus shell. But look through a telescope and you'll see it again in the logarithmic spirals of galaxies like M51. These patterns emerge because nature follows the path of least resistance, optimizing energy and stability, whether it's building a microscopic protein or a million light-year-wide vortex of stars. Even the vibrations of atoms, those tiny quantum hums, resonate like musical notes in a chord harmonics that mirror the rhythmic pulsations of variable stars across the cosmos. Then there are fractals, geometric shapes that repeat themselves at every scale. A lightning bolt's jagged path resembles the branching veins of a leaf, which in turn mirrors the vast cosmic web of galaxies connected by dark matter filaments. Scientists have found that the distribution of matter in the universe follows fractal patterns up to certain scales, as if the universe is echoing its own blueprint. Your brain's neural networks, they branch in the same way, suggesting that the rules governing growth and connection might be universal, whether you're tracing synapses or interstellar gas clouds. What does this symmetry mean? Some physicists argue it's evidence of a deeper, underlying order, a set of primordial rules that apply whether you're studying quarks or quasars. Others see it as nature's way of recycling its most efficient solutions. But perhaps the most profound idea is this: when we recognize these patterns, we're glimpsing the universe's habit of speaking the same language across all dimensions. The spiral of a galaxy and the spin of an electron aren't just vaguely similar, they're two verses of the same cosmic song. Dark matter is the universe's most elusive architect, an invisible force sculpting galaxies while leaving no trace of itself behind. Picture a grand cathedral held together by hidden scaffolding, its beauty visible but its true support unseen. That's how dark matter operates. It doesn't emit, absorb, or reflect light, yet its gravitational pull is so powerful that without it, galaxies would fly apart like unspooled thread. Stars on the outer edges of spiral galaxies rotate far faster than they should, defying the laws of gravity as we understand them, unless there's something we can't see, something massive, anchoring them in place. This cosmic phantom isn't just a placeholder for our ignorance. Its influence echoes the strange behavior of particles at the quantum scale. Take the Higgs field, an invisible energy field that gives particles their mass. Like dark matter, it's everywhere but undetectable without precise instruments. Or consider virtual particles which flicker in and out of existence in empty space, exerting forces we can measure even though they're never directly observed. The parallels are uncanny. Both realms rely on unseen actors to explain the visible world's behavior. Some physicists speculate that dark matter could be more than a galactic glue. It might be a bridge between the quantum and the cosmic. Certain theories propose that dark matter particles interact weakly with ordinary matter through forces we haven't yet discovered, akin to how neutrinos pass through Earth almost unnoticed. Others suggest dark matter could have its own quantum fields, creating subtle ripples that influence the structure of atoms. Imagine a hidden conversation between the smallest particles and the largest structures, mediated by something we're only beginning to sense. The most tantalizing clue: dark matter's distribution in the universe mirrors the fractal patterns found in quantum foam, the turbulent, probabilistic nature of space-time at microscopic scales. Galaxies cluster along vast, web-like filaments of dark matter, a cosmic lattice that looks strikingly similar to the probability clouds of electrons around an atom. If these patterns aren't coincidental, they could hint at a unified framework where the rules of the very small and the very large aren't just similar, they're intertwined. We might be standing at the edge of a revelation. That dark matter isn't merely holding galaxies together, but weaving the fabric of reality itself. Energy flows through the universe like an endless river, transforming from one shape to another without ever disappearing. At the quantum level, particles buzz with an invisible vitality, electrons leap between orbits, photons dart through space, and even the vacuum itself crackles with fleeting bursts of energy. This microscopic dance powers every chemical reaction in your body, every flicker of thought in your brain. But scale up to the cosmic stage, and that same energy takes on breathtaking new forms. A single bolt of lightning carries enough power to illuminate a city, yet it pales beside the fury of a supernova, where a dying star releases more energy in seconds than our sun will emit in its entire lifetime. Einstein's equation E equals mc squared isn't just a formula, it's the universe's greatest magic trick, revealing that matter and energy are two sides of the same coin. The warmth of sunlight on your skin, that's nuclear fusion energy, born when hydrogen atoms in the sun's core collide under crushing pressure, transforming into helium and releasing photons that travel 93 million miles to reach you. Every calorie you consume traces back to plants capturing solar energy, which itself originated in a star's furnace. Even the uranium in nuclear reactors carries energy locked away during the violent deaths of ancient stars, a cosmic inheritance billions of years in the making. The most astonishing part: this energy exchange isn't random, it follows precise, universal laws. Quantum fields vibrate at specific frequencies, like strings on a cosmic instrument, determining the properties of particles and forces. Meanwhile, black holes convert gravitational energy into light with terrifying efficiency, their accretion disks blazing hotter than anything else in the universe. And dark energy, that mysterious force accelerating the expansion of space, might be the ultimate example of energy's versatility, a hidden pressure woven into the fabric of space-time itself. From the spark of a neuron firing in your brain to the slow burn of a galaxy's rotation, energy binds the cosmos together. It's the reason atoms bond, stars ignite, and life emerges. And just as a river flows from mountain springs to the open sea, energy's journey links the smallest quantum events to the grandest celestial phenomena, a never-ending cycle of creation and transformation that hums through every corner of existence. The Higgs field is like the universe's backstage crew, invisible but essential, quietly handing particles their mass while the cosmic show goes on. Picture an actor stepping onto a stage and suddenly moving slower, as if wading through honey. That's what happens when particles interact with this field. Some, like quarks, get sticky and gain mass, while others, like photons, glide through untouched. Without it, atoms wouldn't form, stars wouldn't ignite, and you wouldn't exist. But here's where it gets cosmic. The Higgs isn't alone in its unseen influence. In the first trillionth of a second after the Big Bang, another field in flattened, stretched spacetime faster than light, smoothing the universe into the vast, even expanse we see today. These fields might seem unrelated, one governing particle physics, the other shaping the cosmos, but they share a haunting similarity. Both are thought to be scalar fields, meaning their strength is the same in all directions, like an invisible mist filling every corner of space. When the Higgs field switched on as the universe cooled, it triggered a phase transition not unlike water freezing into ice. Cosmic inflation may have been driven by a similar shift, a sudden drop in energy that released a torrent of expansion. Some theorists even speculate they could be two faces of the same phenomenon, a unified field that dictated both the universe's growth spurt and the mass of everything within it. The echoes don't stop there. Quantum fluctuations in the inflattened field left faint wrinkles in space-time tiny density variations that grew into galaxies. Meanwhile, fluctuations in the Higgs field could explain why we live in a universe with just the right mass for life. Too strong, and atoms would be sluggish; too weak, and matter would never clump together. It's as if both fields were tuned to the same cosmic rhythm, one orchestrating the grand structure of the cosmos, the other fine-tuning the building blocks within it. Could this mean the Higgs and inflaton are threads of a deeper fabric? Experiments like the Large Hadron Collider hunt for signs of heavier Higgs particles, which might hint at connections to inflation. And gravitational wave detectors listen for whispers from the early universe, where traces of these fields' interplay might still linger. If proven, it would reveal a stunning unity, that the force shaping galaxies and the one giving you weight are part of the same cosmic symphony, playing out from the smallest particles to the edges of the observable universe. Quantum entanglement isn't just a laboratory curiosity. It might be the universe's most profound method of communication, operating on scales we're only beginning to imagine. Picture two electrons born from the same event, spinning in perfect sync. Change the spin of one, and the other instantly mirrors that change, even if it's light years away. Einstein famously dismissed this as spooky action at a distance, but experiments have confirmed it's real. Now, scientists are asking an even wilder question. Could this eerie connection stretch across the cosmos, linking galaxies like invisible threads in a cosmic tapestry? The idea isn't as far-fetched as it sounds. In the early universe, particles were packed so tightly that everything was entangled, a dense, interconnected soup of quantum relationships. As space expanded, those particles were flung apart, but their quantum links might have remained, stretched to astronomical scales. Imagine a pair of quasars on opposite sides of the observable universe, their light emitted from regions that were once touching. Some theorists suggest they could still share quantum ties, their properties subtly coordinated across billions of years. If true, the universe isn't just held together by gravity, it's stitched with a hidden quantum fabric. Here's where it gets stranger. Black holes, those cosmic vacuum cleaners, might play a key role. When matter falls into a black hole, its information isn't destroyed but scrambled and radiated back out as Hawking radiation. Some models propose that this process could create entangled particles, with one inside the black hole and one outside. Scale this up, and you could have entire galaxies linked through the quantum echoes of ancient black holes, their fates intertwined in ways we can't yet measure. The implications are staggering. If entanglement spans the cosmos, it could explain why the universe appears so uniform. Distant regions that never had time to exchange light, let alone information, somehow share the same temperature and structure. Cosmic inflation offers one explanation, but quantum entanglement offers another. These regions were once quantum neighbors, and their connection never truly broke. It's as if the universe remembers its origins, its parts whispering to one another across the void. Could we ever prove this? New telescopes and quantum detectors are hunting for clues. Some scientists analyze the cosmic microwave background for patterns that might reveal large-scale entanglement. Others study how entangled particles behave in extreme gravitational fields, simulating conditions near black holes. The answers might reshape our understanding of reality itself, not as a collection of separate objects, but as a single, entangled whole where every particle, every star, every galaxy is part of a vast, instantaneous conversation. The universe isn't just expanding, it might be profoundly, intimately connected in ways we're only beginning to glimpse. Black holes are the universe's ultimate paradox regions where gravity wins its fiercest battle, crushing matter into a point of infinite density called a singularity. Picture taking the entire mass of a star 20 times heavier than our Sun and squeezing it into a space smaller than a single atom. At this unimaginable core, the laws of physics as we know them break down. Time stops, space curls inward, and yet this terrifying extreme might hold a mirror to the very beginning of everything. The Big Bang itself erupted from a singularity, a moment when all the energy, matter, and dimensions of the cosmos were compacted into an infinitely hot, dense speck. One marked the birth of the universe, the other signifies matter's final collapse. The symmetry goes deeper. Just as a black hole's singularity is shrouded by an event horizon, a point of no return for light and matter, the early universe had its own cosmic horizon. In the first fleeting instance after the Big Bang, space expanded faster than light could traverse it, creating regions forever cut off from one another. Today, we observe this as the cosmic microwave background, the faint afterglow of that primordial fireball. But here's the twist. Some physicists speculate that a black hole's interior might resemble an inverse Big Bang, a realm where space and time flip roles. Fall past the event horizon, and time becomes as directional as space is for us, funneling you inevitably toward the singularity. It's as if the universe encoded its origin story in the very monsters it creates. What happens inside a singularity? General relativity predicts infinite density, but quantum mechanics suggests particles resist such crushing confinement. This clash hints at a deeper truth that singularities might be portals to something beyond our current understanding. String theory proposes they could unravel into higher dimensional bridges called wormholes, while loop quantum gravity imagines them rebounding in a cosmic bounce. Remarkably, these theories echo ideas about the Big Bang's own singularity, which some models suggest could have been a rebound from a previous universe's collapse. If correct, black holes might not be endpoints, but waypoints in an endless cycle of creation and destruction. The most tantalizing clue lies in Hawking radiation, the faint glow black holes emit as they slowly evaporate. This process links quantum mechanics and gravity, two forces otherwise at odds. As a black hole radiates away its energy, it might leave behind a relic, a tiny, dense remnant resembling the universe's infancy. Some scientists even speculate these relics could seed new universes, their singularities birthing new cosmic expansions. Imagine a black hole in our universe becoming the Big Bang of another, like a cosmic Russian nesting doll. From the infinitely small to the infinitely large, singularities remind us that the universe might not have edges, only transformations. Whether in the heart of a black hole or the spark of creation, these extremes challenge us to rethink the nature of reality itself, not as a linear timeline, but as a tapestry woven from cycles of collapse and rebirth. The same forces that compress stars into oblivion might also hold the secret to how everything began. Neutrinos are the universe's shadowy couriers, particles so elusive they can sail through a light year of lead without a single collision. Every second, trillions of them pass through your body like cosmic ghosts, unfelt and unseen. born in the nuclear furnaces of stars, the violent deaths of supernova, and even the Big Bang's afterglow. These phantoms carry whispers from the most extreme places in existence. What makes them extraordinary isn't just their stealth, it's how they thread the needle between the infinitesimal and the infinite. A single neutrino interacts so weakly with matter that it might cross the entire observable universe unchanged, yet its properties are governed by the same quantum rules that dictate how electrons behave in an atom. Take the supernova that lit up Earth's skies in 1987. Hours before visible light reached us, detectors buried deep underground caught a fleeting burst of neutrinos. These particles had raced ahead at nearly the speed of light, unhindered by the collapsing star's dense outer layers, while photons took hours to fight their way free. That neutrino pulse was more than a cosmic alert. It was a direct transmission from the heart of a dying star, proof that these particles bridge scales in ways no other messenger can. Today, observatories like IceCube in Antarctica hunt for neutrinos from black holes and merging neutron stars, turning Earth itself into a telescope for invisible signals. The deeper mystery lies in how neutrinos oscillate, changing their identity between three types as they travel. This quantum shape shifting implies they have mass, a revelation that upended physics and hinted at undiscovered particles lurking beyond our current models. Some theories suggest neutrinos might hold clues to why the universe is made of matter rather than antimatter, a cosmic imbalance that allowed galaxies and us to exist. Others propose they could be tied to dark matter, their faint gravitational pull subtly shaping the cosmos. Here's the astonishing part: neutrinos might be stitching together the fabric of reality itself. Quantum field theory suggests that every particle is a ripple in an invisible field, like a wave on an ocean. Neutrinos, barely interacting with those fields, skim across the surface of this cosmic sea, feeling only the faintest tug of gravity. Yet their sheer numbers, outnumbering atoms by 1,000,000,000 to 1, mean they could be weaving an unseen lattice, a background hum influencing everything from galaxy formation to the stability of atomic nuclei. Detecting them requires both ingenuity and patience. Experiments like Japan's Super Kamiok and use colossal tanks of ultra-pure water, waiting for the rare flash of light when a neutrino collides with an atom. These moments are like catching a single raindrop in a storm, but each one carries a story. Some neutrinos arriving today were forged in the first seconds after the Big Bang, their journeys spanning 13.8 billion years. Others bear the fingerprints of distant quasars or the chaotic cores of active galaxies. In their silence, neutrinos speak volumes. They remind us that the universe communicates in more ways than light, and that the tiniest particles can hold the grandest narratives. From the quantum flutter in an atom to the explosive death of a star, they're the invisible threads tying the cosmos together, a reminder that even the most fleeting messengers can carry the weight of eternity. Every time a high-energy cosmic ray slams into Earth's atmosphere, it sets off a microscopic fireworks show, one that's been shaping the chemistry of our planet for billions of years. These aren't ordinary particles, they're bullets fired from cosmic accelerators like supernova and black holes, traveling at nearly the speed of light. When they strike an air molecule, the collision is so violent it shatters atoms, creating cascades of secondary particles that rain down toward the surface. This process, called an air shower, transforms simple elements into rare isotopes and even influences the formation of clouds. It's a direct link between the most cataclysmic events in the universe and the air you're breathing right now. Take carbon-14, the radioactive isotope used to date ancient artifacts. It shouldn't exist naturally in Earth's atmosphere, except cosmic rays keep making it. When a high-energy proton from deep space collides with a nitrogen atom, it knocks out a neutron, converting nitrogen into carbon-14. This isotope gets woven into plants, animals, and eventually you, carrying a timestamp of cosmic activity. Without these collisions, archaeology would lose one of its most powerful tools, but the influence goes further. Cosmic rays ionize molecules in the air, creating pathways for lightning to form. Some scientists argue they might even seed low-level clouds, subtly affecting weather patterns by altering how water vapor condenses, the most astonishing part. These particles carry fingerprints of their origins, ultra-high-energy cosmic rays, some packing the kinetic energy of a fastball in a single particle, are so powerful they shouldn't exist under known physics. Yet detectors like the Pierre Auger Observatory in Argentina have caught them, their trajectories pointing back to voids between galaxies where no known cosmic accelerators reside. It's as if the universe is hiding unimaginable engines in the emptiest places, flinging particles with forces we can't yet explain. On the quantum scale, these collisions reveal another layer of strangeness. When a cosmic ray hits an atomic nucleus, it can briefly create particles that haven't existed since the Big Bang, exotic matter like pions and muons that decay in microseconds. These fleeting visitors are like echoes of the early universe, reminding us that the same violent processes shaping galaxies are also at work in the thin veil of our atmosphere. Even the neutrinos we discussed earlier owe some of their numbers to cosmic ray interactions, which produce them in showers alongside other secondary particles. This invisible rain connects us to the cosmos in ways we're only beginning to grasp. The same forces that sculpted galaxies and forged stars are still at work today, rewriting Earth's atomic story one collision at a time. From the radiocarbon in your bones to the charge in a thunderstorm, cosmic rays prove that the boundary between out there and down here is far thinner than it seems. The universe isn't just above us, it's already here, woven into the fabric of our world. The same invisible glue that holds atomic nuclei together might also be shaping the largest structures in the cosmos, a staggering thought when you consider the scales involved. The strong nuclear force, which locks quarks into protons and neutrons, operates over distances smaller than an atom's core. Yet its fingerprints could be faintly visible in the way galaxies cluster together across millions of light years. Both forces, strong and gravitational, share a common purpose, taming chaos into order. Without the strong force, atomic nuclei would fly apart in a flash of repelling positive charges. Without gravity's relentless pull, galaxies would scatter like dust in the wind. But could there be a deeper connection hiding in plain sight? Let's break it down. The strong force is 100 times more powerful than electromagnetism and 1,000,000 trillion times stronger than gravity. It's so potent that quarks, the building blocks of protons, can never escape one another completely. Stretch them apart, and the energy stored in their gluon bonds, the particles mediating the strong force, creates new quarks before they can separate. It's nature's ultimate failsafe, ensuring atomic stability. Now zoom out to galaxy clusters where gravity performs a similar trick. Galaxies orbit one another in vast, slow dances, bound by an invisible web of dark matter and curved spacetime. Just as quarks are trapped in protons, galaxies are trapped in clusters, their escape velocity too high to overcome. Here's where the parallels get eerie. Both forces weaken with distance but never truly vanish. The strong force drops off exponentially, yet its effects linger just enough to keep nuclei intact. Gravity weakens with the square of the distance, yet its reach is infinite, shaping the cosmos over eons, and both seem to favor groups of three. In quantum chromodynamics, the theory describing the strong force, quarks prefer trios like the 2 up and 1 down quark in a proton. Meanwhile, galaxy clusters often organize into triple systems, with massive galaxies anchoring smaller companions in stable configurations. Is this numerology or a hint of universal patterns repeating? The most tantalizing clue comes from string theory, which suggests all forces might unify at unimaginable energies. In the early universe's first microseconds, temperatures were so high that the strong and electroweak forces might have behaved as one. Some models propose that remnants of this unity could manifest in large-scale structures, with gravity mimicking aspects of nuclear binding on cosmic scales. It's speculative, but consider this. Just as the strong force creates mesons to mediate interactions between protons, could dark matter act as a cosmic glue, transmitting gravitational influence between galaxies in ways we don't yet understand? We're left with a breathtaking possibility that the laws governing the tiniest particles and the largest structures aren't just similar but fundamentally linked. The same mathematical tools used to model quark confinement in particle accelerators might one day explain why galaxies cling together in clusters. Whether through hidden symmetries, higher dimensions, or undiscovered fields, the universe seems to whisper that its forces are chapters in a single story, one we're only beginning to read. Superconductors seem to defy logic, materials that, when chilled to extreme temperatures, let electricity zip through them forever without losing a single watt to resistance. It's like a highway with zero friction where electrons pair up and glide effortlessly, as if the rules of physics took a holiday. But this isn't just a lab curiosity. Out in the cosmos, there might exist something eerily similar: cosmic strings, hypothetical cracks in space-time left over from the universe's fiery birth. These aren't your everyday flaws. They're thought to be unimaginably thin yet denser than a neutron star, stretching across light years like invisible guitar strings. And just as superconductors carry current without loss, cosmic strings could channel energy so perfectly they'd leave even the best human-made materials in the dust. The parallels run deeper than you'd think. In a superconductor, electrons overcome their natural repulsion by forming Cooper pairs, linked through vibrations in the material's atomic lattice. Cosmic strings, if they exist, might also rely on paired behavior, twists in the fabric of space-time so stable they've survived since the first trillionth of a second after the Big Bang. Some theories suggest these strings could vibrate at specific frequencies, emitting gravitational waves or even creating odd distortions in the light from distant galaxies like cosmic mirages. Astronomers have searched for these telltale warps, though no smoking gun has appeared yet. Then there's the energy factor. Superconductors can levitate magnets in midair, locking them in place with quantum precision, a phenomenon called the Meissner effect. Cosmic strings could wield similar control on a galactic scale, their immense gravitational fields warping the paths of stars and gas clouds around them. Imagine a string thinner than a proton but with the mass of a mountain range, slicing through a galaxy like a wire through cheese. Its pull would be so concentrated that anything passing nearby would get a gravitational kick, potentially sending stars hurtling at bizarre angles. Here's where it gets speculative and thrilling. Some physicists propose that cosmic strings could be superconducting themselves, coursing with primordial currents from the early universe. If true, they'd be the ultimate energy conduits, potentially powering some of the most violent phenomena we see, like fast radio bursts or gamma-ray jets. It's a wild idea, but not entirely without precedent. In the lab, scientists have created synthetic defects in materials that mimic cosmic strings' predicted behavior, and weirdly, these defects sometimes exhibit superconducting properties. Could the universe have baked its own version into space-time itself? The hunt for cosmic strings isn't just about validating a theory, it's about uncovering a possible bridge between quantum perfection and cosmic structure. If they're real, these filaments could help explain why the universe isn't perfectly smooth, why matter clumped into galaxies instead of spreading evenly. And if superconductors here on Earth hint at their behavior, we might be closer to understanding spacetime's hidden circuitry than we realize. From the quantum dance of paired electrons to the gravitational thrum of hypothetical strings, the universe seems obsessed with flawless flow, whether it's electricity or the very fabric of reality. Plasma isn't just another state of matter. It's the universe's default setting, the fiery canvas on which stars, galaxies, and even lightning paint their stories. Over 99% of the visible cosmos exists as plasma, a seething sea of ionized atoms where electrons break free from their nuclei, creating a roiling mix of charged particles. Look at the sun and you're seeing plasma in its most primal form, a churning ball of hydrogen and helium so hot that atoms can't hold onto their electrons. But step into your kitchen and you'll find it again in the soft glow of a neon light, where a tiny spark transforms inert gas into a shimmering ribbon of ionized color. This isn't just coincidence, it's proof that the same physics governing the hearts of stars also flicker in our everyday devices. The sun's corona, that wispy halo visible during a solar eclipse, is a plasma masterpiece. Heated to millions of degrees, it defies intuition by growing hotter as it stretches farther from the sun's surface, a mystery scientists are still unraveling. This superheated plasma doesn't just sit still, it erupts in solar flares and coronal mass ejections, hurling charged particles across the solar system. When these particles collide with Earth's magnetic field, they trigger the aurora's nature's own plasma light show, where oxygen and nitrogen atoms glow like celestial neon signs. But the cosmos doesn't stop there. Between the stars, the interstellar medium is a diffuse plasma, so thin that a teaspoon of it might contain just a few atoms, yet it's the raw material for new stars and planets. Back on Earth, plasma is the unsung hero of modern technology. Fusion reactors like ITER aim to replicate the sun's energy production by squeezing hydrogen plasma under crushing magnetic fields, a process that could unlock near-limitless clean power. Meanwhile, plasma TVs, though now vintage, used to bathe living rooms in light by exciting tiny pockets of gas, and industrial plasma cutters slice through metal with precision by focusing ionized gas into jets hotter than lava. Even your smartphone's microchips likely owe their existence to plasma etching, where ionized gas carves intricate circuits thinner than a human hair. The real magic lies in plasma's dual nature. At cosmic scales, it's a conductor of magnetic fields, shaping galaxies and birthing stars. At quantum scales, it's a playground for waves and instabilities, where particles interact in ways that challenge our understanding of matter. This duality makes plasma a bridge between the infinitesimal and the infinite, a reminder that the universe loves recycling its most fundamental tricks. Whether in the heart of a star or the glow of a neon sign, plasma proves that the boundaries between natural and man-made are far blurrier than we think. Neutron stars are the universe's ultimate atomic overachievers, stellar corpses so dense that a single teaspoon of their material would weigh 1 billion tons on Earth. Picture taking the entire mass of our sun and crushing it into a sphere no wider than Manhattan. The result, a cosmic object where the rules of atomic physics stretch to their breaking point, creating conditions so extreme they blur the line between the infinitesimal and the astronomical. At their cores, neutron stars are essentially gigantic atomic nuclei, but scaled up to celestial proportions. The same strong nuclear force that binds protons and neutrons inside an atom's heart now operates across kilometers of ultra-compressed matter, turning what was once a star into something more akin to a single, monstrous atom. How does this mind-bending density happen? When a massive star exhausts its nuclear fuel, it collapses under its own gravity in a supernova explosion. The outer layers blast away in a spectacular light show, but the core implodes with such force that electrons and protons fuse into neutrons, leaving behind a city-sized orb of pure neutron matter. This stuff isn't just dense, it's a quantum fluid unlike anything on Earth, where neutrons pack together so tightly they start behaving like a superfluid, flowing without friction. Some neutron stars even develop crusts of iron nuclei squeezed into crystalline lattices, floating atop an ocean of degenerate neutrons. It's as if the periodic table got pushed into overdrive, forging materials that defy imagination. Parallels to atomic nuclei don't stop there. Just as protons and neutrons in a nucleus arrange themselves into energy levels called shells, neutron stars may have layered interiors with distinct quantum behaviors. Theorists speculate about exotic phases like nuclear poster, where matter forms shapes resembling spaghetti or lasagna under unimaginable pressure. And just as atomic nuclei can vibrate or rotate, neutron stars spin at dizzying speeds, some whirl hundreds of times per second, their surfaces moving at a fraction of light speed. These pulsars act like cosmic lighthouses, beaming radiation across the galaxy with precision rivaling atomic clocks. What's truly astonishing is how neutron stars bridge scales. The same quantum mechanics governing particles in a lab also dictates the structure of these stellar giants. Their magnetic fields, trillions of times stronger than Earth's, arise from quantum processes amplified to cosmic proportions. Even their gravitational fields, so intense they bend light into halos, echo the curvature of space-time near black holes. Yet they remain just barely tangible, with surfaces you could theoretically stand on if not for the crushing gravity. These stellar oddities aren't just curiosities, they're natural laboratories for testing physics at its limits. When two neutron stars collide, the resulting kilonova explosion forges heavy elements like gold and platinum, scattering them across the cosmos. Gravitational wave detectors have caught these collisions, revealing ripples in spacetime that carry secrets about nuclear matter's behavior. Meanwhile, observations of pulsars help refine our understanding of quantum fluids and even dark matter's distribution. In neutron stars, the universe demonstrates its flair for recycling patterns. The forces that hold atoms together also sculpt some of its most enigmatic objects, proving that the macro and micro aren't separate realms, just different verses of the same cosmic song. From the nucleus of an atom to the heart of a stellar corpse, the same physics whispers across scales, binding the universe together in ways we're only beginning to decode. Pulsars are nature's most precise timekeepers, celestial metronomes ticking with such regularity, they rival the atomic clocks in our most advanced laboratories. Imagine a star the size of a city, spinning faster than a kitchen blender, its beams of radio waves sweeping across the cosmos like a lighthouse beam cutting through fog. Each rotation is so consistent that some pulsars, especially millisecond pulsars, which spin hundreds of times per second, deviate by less than a billionth of a second over decades. This isn't just cosmic spectacle, it's a direct echo of the quantum realm, where atoms like cesium or hydrogen oscillate between energy levels with similar precision, forming the basis of human timekeeping. What makes pulsars so staggeringly accurate? It all comes down to their unbelievable density and angular momentum. When a massive star collapses into a neutron star, it retains much of its original rotational energy, but now squeezed into an object with a diameter smaller than the length of Manhattan. Like a figure skater pulling in their arms to spin faster, this compression sends the star's rotation rate skyrocketing. The resulting pulsar's magnetic field, trillions of times stronger than Earth's, channels particles into beams radiating from its magnetic poles. If these poles are misaligned with its spin axis, which they almost always are, the beams sweep across space like cosmic searchlights, appearing to blink on and off from our perspective. The parallels to atomic clocks are uncanny. Both rely on fundamental, unchanging properties. For pulsars, it's the conservation of angular momentum keeping their spin stable. For atoms, it's the fixed energy gaps between electron orbitals. Atomic clocks measure time by counting the oscillations of cesium atoms, 9,192,630,1770 vibrations per second define the official second. Pulsars, in their own way, do something similar, with each rotation marking another tick in a timescale far grander than anything humans have engineered. Scientists have harnessed pulsars' precision for extraordinary purposes. The Arecibo Observatory once used a pulsar's pulses to test Einstein's theory of general relativity, confirming that gravitational waves stretch and compress spacetime exactly as predicted. More recently, astronomers proposed using networks of pulsars as galaxy-sized gravitational wave detectors, their rhythmic pulses subtly distorted by passing ripples in spacetime. There's even the Pulsar Navigation Project, where spacecraft could triangulate their position in deep space by comparing pulsar signals, much like GPS satellites, except these beacons are millions of light-years apart and require no maintenance. Yet pulsars aren't perfect. Over millennia, they slow down as their radiation beams carry away energy, a process called spin-down. Some, like the Crab pulsar, are young and erratic, their rotations jittering like a scratched record. Others, especially those rejuvenated by stealing matter from a companion star, settle into rhythms so stable they could outpace atomic clocks over centuries. This diversity mirrors the quantum world, where some atomic transitions are rock solid while others are sensitive to disturbances. In their relentless ticking, pulsars bridge the gap between the quantum and the cosmic. They remind us that the same principles governing electrons jumping between energy levels also steer the spin of stellar corpses light years away. From the vibrations of atoms to the pulses of dying stars, the universe keeps time in ways both vast and minuscule, a silent symphony of rhythm stretching across every scale of existence. Beneath the smooth fabric of spacetime we perceive lies a hidden turbulence, a frothing, chaotic sea known as quantum foam. Imagine zooming in on the universe until even atoms seem vast, descending to scales so small that distances become meaningless. Here at the Planck length, a size a trillion times tinier than a proton, spacetime itself loses its smoothness, churning with fleeting bubbles of energy. Virtual particles pop in and out of existence, borrowing energy from the vacuum like cosmic defrauders, only to vanish before nature can collect its debt. This isn't just theoretical whimsy. It's the boiling undercurrent of reality, where the very concepts of here and now dissolve into uncertainty, the wildest part. This microscopic frenzy might leave fingerprints on the cosmos at large. Just as ripples in a pond can amplify into waves, quantum fluctuations in the early universe might have stretched during cosmic inflation, seeding the vast web of galaxies we see today. The same randomness that makes a single electron's path unpredictable could have dictated where galaxy clusters formed billions of years later. It's as if the universe saved a receipt from its tiniest transactions and cashed it in on the grandest scales imaginable. Some theories take this further, proposing that quantum foam could warp light traveling across the cosmos. photons from distant quasars, having journeyed billions of light years, might carry subtle scars from brushing against spacetime's granular texture. Astronomers have hunted for this effect by analyzing gamma-ray bursts, the universe's most energetic flashes, for signs of delayed high-energy photons, as if the foam were a cosmic sieve slowing some light more than others. So far, the evidence is elusive, but the search continues because if proven, it would mean that the universe's largest and smallest structures aren't just connected, they're in constant, invisible conversation. Then there's the black hole connection. At a singularity's edge where gravity warps spacetime beyond recognition, quantum foam might become so turbulent it resembles whitewater rapids. Some models suggest this frenzy could prevent true singularities from forming, replacing them with a roiling quantum fuzzball, a state where matter and spacetime blur into a single, churning entity. If correct, black holes wouldn't be the universe's ultimate dead ends, but portals to a realm where quantum foam reigns supreme, its behavior echoing the primordial chaos of the Big Bang itself. What does this mean for us? On Earth, quantum foam is too fleeting to notice, its effects drowned out by the stability of atoms and the pull of gravity. Yet in particle colliders, scientists glimpse its shadow when particles collide at near light speeds, their interactions hinting at spacetime's grainy underpinnings. And in the quiet hum of the cosmos, the faintest whispers of this foam might still resonate, a reminder that the universe's foundations are far stranger and far more interconnected than they appear. From the Planck scale to the cosmic web, the same quantum restlessness shapes reality, stitching the infinitesimal to the infinite with threads of pure uncertainty. In a lab chilled to within a whisper of absolute zero, something extraordinary happens. Atoms slow down so much that they merge into a single quantum wave, a state called a Bose-Einstein condensate. It's as if trillions of individual particles forget their identities and begin acting as one, like a crowd synchronizing into a perfectly choreographed dance. This isn't just a curiosity of ultra-cold physics. It might hold the key to one of the universe's biggest mysteries: dark energy, the enigmatic force accelerating the expansion of space itself. To understand why, picture how a Bose-Einstein condensate forms. When atoms are cooled to temperatures just billionths of a degree above absolute zero, their quantum wavelengths stretch and overlap until they become indistinguishable. The result is a new phase of matter where quantum effects, normally hidden in the microscopic world, manifest on visible scales. Now imagine a similar phenomenon occurring not in a lab, but in the vacuum of space, a sea of quantum fields so uniform and pervasive that it exerts a gentle but unstoppable pressure, pushing galaxies apart. That's the essence of one leading theory about dark energy. It could be a cosmic-scale Bose-Einstein condensate, a quantum whisper stretched across the entire universe. The parallels don't stop there. Just as a lab-made condensate generates bizarre behaviors like superfluidity, where liquid helium defies gravity to climb walls, dark energy might arise from a quantum fluid permeating spacetime. Even stranger, some models suggest this fluid could have negative pressure, a property that would explain why it drives the universe to expand faster over time. It's as if the vacuum itself is a superfluid with built-in antigravity, its quantum froth nudging galaxies apart like leaves on a rising tide. Critics argue the comparison isn't perfect. Dark energy's effects are unimaginably weaker than the forces in a lab condensate, and its source remains speculative, yet the underlying principle, that quantum collective behavior can scale from atoms to the cosmos, is tantalizing. After all, the same quantum mechanics that governs electrons in an atom also dictates the fate of the universe. If Bose-Einstein condensates show us how local quantum unity can emerge, perhaps dark energy is the ultimate expression of that unity, a reminder that the universe's largest and smallest scales are bound by the same invisible threads. Experiments are already probing this connection. By studying how condensates behave under extreme conditions, physicists hope to uncover clues about dark energy's nature. Meanwhile, telescopes map the universe's expansion with ever greater precision, searching for fluctuations that might reveal dark energy's quantum origins. Whether or not the link holds, the pursuit underscores a profound truth. The universe loves recycling its most elegant ideas, from the frigid quiet of a lab to the endless stretch of spacetime itself. The holographic principle turns our understanding of reality inside out literally. Imagine the entire universe, from swirling galaxies to the cells in your body, functioning like a movie projected from a cosmic film reel. Except instead of a three-dimensional world, everything we see and experience could be encoded on a distant two-dimensional surface, like information etched onto the event horizon of a black hole. This isn't science fiction. It's a serious theory born from the clash between quantum mechanics and gravity, suggesting that the three-dimensional world we perceive might just be an elaborate illusion. The idea first emerged when physicists studying black holes stumbled upon a paradox. According to quantum mechanics, information can never be destroyed, yet black holes seem to erase it completely when matter crossed their event horizons. The solution: the information isn't lost. It's smeared across the black hole's surface like a celestial fingerprint, preserved in a 2D code. Extend this logic to the entire universe, and you get the holographic principle. Every particle, every force, every cosmic structure could be a projection of data stored on some unimaginably vast boundary at the edge of spacetime. Think of it like a credit card hologram. Tilt the card, and a 3D image seems to float above the surface, even though all the information is actually embedded in the flat, shiny strip. Similarly, the universe might tilt reality in a way that makes depth, volume, and time feel tangible, even if they're just shadows of a deeper, flatter truth. This would mean that the atoms in your hand and the stars in the sky aren't fundamentally three-dimensional. They're more like pixels in a cosmic display, rendered in real time from a hidden source code. The implications are staggering. If the holographic principle holds, it would mean that space itself is an emergent property, not a fundamental one. The smooth, continuous expanse we move through could be a kind of collective hallucination, stitched together by quantum entanglement, those spooky, instantaneous connections between particles we explored earlier. Even time might lose its status as a fixed arrow, becoming another layer of the projection. Some theorists suggest that this could solve long-standing puzzles, like why gravity is so weak compared to other forces. If gravity leaks into our 3D world from a 2D surface, it might arrive diluted, like a signal losing strength as it travels. Experiments are already probing this wild idea. Fermilab's holometer, for instance, hunts for faint jitters in spacetime that could hint at a pixelated universe. Meanwhile, studies of the cosmic microwave background, the afterglow of the Big Bang, search for patterns that might reveal an underlying holographic code. So far, the evidence is inconclusive, but the search itself is reshaping how we think about reality. Whether the holographic principle is confirmed or not, it forces us to confront a profound possibility: that the universe's deepest truths might not lie in the dimensions we experience, but in a hidden, interconnected script written at the edges of perception. From the tiniest quarks to the largest galaxy clusters, everything might be part of a cosmic projection, a hologram so vast and intricate that even the projector is part of the show. Look closely at a frost crystal forming on a window pane. and you'll see jagged branches splitting again and again, tiny mirrors of the sprawling river deltas seen from space. This isn't just visual poetry, it's a signature written into the fabric of reality. Fractals, those infinitely complex patterns repeating at every scale, appear everywhere, from the branching of neurons in your brain to the vast cosmic web of galaxies. What's astonishing isn't just their ubiquity, but what it implies. The universe might be running on a hidden algorithm, generating boundless complexity from startlingly simple rules. Take the humble fern. Each frond divides into smaller copies of itself, and those divide again, creating a structure where any tiny segment resembles the whole. Zoom out, and you'll find the same pattern in mountain ranges, coastlines, even the turbulent swirls of Jupiter's storms. But the real shock comes when astronomers map the distribution of galaxies. Instead of scattered randomly, they cluster along filaments, threads of dark matter, weaving a cosmic net that looks eerily like the branching veins of a leaf or the capillaries in your lungs. The similarities aren't superficial. Mathematically, the clustering follows the same power laws, as if nature has a favorite blueprint it reuses from the microscopic to the galactic. This self-similarity hints at something profound. The universe might not just contain fractals, it might be fractal. Some theories suggest the Big Bang didn't create a single, smooth cosmos, but an infinite cascade of universe bubbles, each with its own physics, nested like Russian dolls. Others propose that spacetime itself has a fractal geometry at quantum scales, a foamy structure that smooths out into the universe we perceive. Even the flow of energy follows fractal pathways. Lightning bolts fork like tree roots, and blood vessels optimize oxygen delivery using the same branching math that galaxies use to distribute matter. Here's where it gets wild. Computer simulations show you can generate realistic galaxies using fractal algorithms no more complex than those modeling snowflakes. Start with a few basic rules: gravity, rotation, and a pinch of randomness, and let the simulation run. Over time, spirals and clusters emerge organically, mimicking Hubble telescope images. This suggests the universe might not need a meticulous architect, just simple, recursive processes playing out over eons. But why does nature love fractals so much? Efficiency. Fractals maximize surface area and minimize energy use. Your lungs pack a tennis court's worth of surface into your chest by branching fractally. Trees optimize sunlight capture the same way. On cosmic scales, the universe's fractal web may be the most efficient way to funnel matter into galaxies, stars, and planets, a cosmic recycling system written in geometry. The most tantalizing question remains: is this pattern evidence of a deeper computational layer to reality? Some physicists speculate that fractals could be shadows of a universe built from information, where spacetime is pixelated and physical laws are emergent algorithms. Whether that's true or not, one thing's certain: from the swirl of your fingerprints to the grandest structures in existence, the universe keeps signing its work with the same elegant, infinitely repeating flourish. Picture a perfectly smooth pond on a windless morning, its surface so uniform you can't tell one side from the other. That's how the universe began, a hot, dense soup where all forces were one, all particles indistinguishable, a state of perfect symmetry. But just as a pond freezes into jagged ice, the infant cosmos underwent transformations that shattered its pristine uniformity, forging the diversity we see today. This process, called symmetry breaking, didn't just shape atoms and galaxies, it wrote the recipe for existence itself. The first critical break happened a fraction of a second after the Big Bang, as the universe cooled from trillions of degrees. Like steam condensing into water, the unified superforce fractured into the four fundamental forces we know: gravity, electromagnetism, and the strong and weak nuclear forces. Each split carved new rules into reality. The strong force locked quarks into protons and neutrons, while electromagnetism orchestrated the dance of electrons. These transitions weren't gradual, they were sudden phase shifts, akin to water molecules snapping into crystalline order as ice forms. In particle accelerators, scientists recreate these moments by smashing atoms to extreme energies, watching as symmetry temporarily restores itself in the debris, offering glimpses of the universe's primordial unity. Material science reveals eerie parallels. When a magnet heats past its Curie point, its atomic spins randomize, erasing its magnetic field, a symmetry restored by energy. Cool it again and spins spontaneously align, breaking symmetry to create new properties. The universe did the same, but on a cosmic scale. The Higgs field's emergence was one such break. As space-time cooled, this invisible molasses gave particles mass, distinguishing light photons from heavy electrons. Without this rupture, atoms couldn't form and stars would never ignite. The most dramatic breaks may have seeded cosmic structure itself. Quantum fluctuations during inflation, tiny random ripples, were frozen into space-time as symmetry breaking unfolded. These microscopic wrinkles stretched to galactic proportions, becoming the gravitational wells where matter pooled into galaxies. It's as if the universe's tiniest shivers programmed the locations of future superclusters. Yet mysteries linger. Why did symmetries break unevenly, leaving us with more matter than antimatter? Why do forces have such disparate strengths? Each imbalance was a cosmic roll of the dice, and the outcomes built a universe capable of hosting life. From the quantum to the cosmological, symmetry breaking reminds us that perfection is sterile. It's the cracks in the mirror that let complexity bloom. Deep inside the sun's core, where temperatures soar to 15 million degrees and pressures crush atoms together like cosmic sumo wrestlers, a quantum magic trick makes life on Earth possible. Protons, which should repel each other due to their positive charges, somehow fuse into helium, releasing the energy that bathes our planet in light. Classically, this shouldn't happen. The electrostatic barrier between protons is like a mountain neither has the energy to climb. Yet fusion occurs constantly, and the reason lies in one of quantum mechanics' most mind-bending phenomena, tunneling. Think of quantum tunneling as a cosmic cheat code. In our everyday world, if you roll a ball toward a hill too steep to crest, it'll roll back every time. But in the quantum realm, particles like protons don't play by those rules. Thanks to wave-particle duality, there's always a tiny probability they'll simply appear on the other side of an energy barrier, as if the hill had a hidden tunnel. It's not that they sneak through, it's that their wave functions, which describe their probable locations, extend slightly into the barrier. Occasionally, that flicker of probability becomes reality. This isn't just theoretical. Without tunneling, stars would be dark. The sun's core protons lack the thermal energy to overcome their mutual repulsion classically. But tunneling allows them to bypass that barrier sporadically, making fusion and starlight possible. In fact, our sun's fusion rate is so sensitive to tunneling that if the phenomenon were slightly weaker, stars might never ignite. A universe without tunneling could be a cold, lifeless void. The implications stretch beyond stellar engines. Tunneling shapes technology too. Your computer's flash memory relies on electrons tunneling through thin, insulating layers to store data. Scanning tunneling microscopes image individual atoms by exploiting tunneling currents, letting us see at scales light microscopes can't reach. Even radioactive decay, where alpha particles tunnel out of unstable nuclei, hinges on this effect. Yet tunneling's wildest role might be cosmic. Some theories suggest vacuum fluctuations, particle pairs popping in and out of existence, could allow tunneling on macroscopic scales. Imagine a neutron star tunneling through an energy barrier to become a quark star, or space-time itself tunneling into a new configuration. While these ideas remain speculative, they underscore tunneling's universal reach, from powering stars to potentially rewriting spacetime's rules. The next time sunlight warms your skin, remember, it's the ghostly hand of quantum mechanics at work, weaving the fabric of reality one improbable tunnel at a time. Gravitational waves and quantum ripples might seem worlds apart, one sculpted by colliding black holes with the mass of entire suns, the other by electrons flitting through the fuzzy edges of probability. Yet both are cosmic messengers carrying whispers of reality's hidden architecture. When LIGO detected its first gravitational wave in 2015, the signal, a barely perceptible wobble in spacetime, told the story of two black holes spiraling into each other over 1 billion light-years away. The distortion they created was minuscule, stretching and squeezing Earth's 4-kilometer-long detectors by less than 1,000th of a proton's width. But that faint tremor confirmed Einstein's century-old prediction: the universe isn't a static stage, it's a dynamic fabric that can stretch, warp, and even ring like a drum. Now shrink that concept down to the quantum realm. Here, particles don't follow neat paths but exist as clouds of probability, their positions and momenta described by undulating wave functions. When you measure an electron's position, you're not locating a tiny ball but collapsing this probability wave, a ripple in the quantum field as real as LIGO spacetime jiggles, just operating on scales 1 trillion times smaller. Recent experiments with entangled particles have even shown how measuring one can instantly alter the probability field of its partner, no matter how far apart they are, an action that, like gravitational waves, transcends distance through invisible connections. The parallels run deeper. Both phenomena reveal forces acting through emptiness. Gravitational waves traverse the cosmos unimpeded, passing through planets and stars as if they weren't there. Quantum waves, too, ignore classical barriers, tunneling through energy walls like ghosts walking through walls. And just as colliding black holes emit gravitational waves with specific frequencies, chirps that LIGO converts into audible sound, quantum systems resonate at distinct energy levels, their wave patterns humming like microscopic musical notes. What's truly astonishing is how these waves bridge scales. The same mathematics describing ripples in spacetime near merging neutron stars can model electron behavior in a hydrogen atom. Some theorists speculate that spacetime itself might emerge from quantum entanglement's web, a hypothesis suggesting gravitational waves could be the macroscopic echoes of microscopic quantum links. If true, then every time LIGO catches a black hole merger, we're not just hearing the universe's grandest events, we're eavesdropping on the quantum whispers that underpin it all. From the violent dance of black holes to the delicate flutter of electrons, waves remind us that reality is never truly still. Whether stretching across galaxies or confined within atoms, these undulations shape everything from the birth of stars to the stability of matter. And with each new detection, whether from gravitational observatories or quantum labs, we're learning to read the universe's hidden language, one ripple at a time. The idea that our universe might be just one page in an infinite cosmic library is more than science fiction. It's a serious possibility emerging from two of physics' most profound theories. On the quantum scale, the many worlds interpretation suggests every decision, every random event, spawns new branches of reality. At the same time, cosmic inflation paints a picture of bubble universes endlessly budding off an ever-expanding spacetime foam. But what if these aren't separate ideas? What if they're different lenses on the same staggering truth that existence is fundamentally multiple? Let's start with quantum superposition. the bizarre phenomenon where particles exist in multiple states until observed. In the lab, an electron can spin both clockwise and counterclockwise simultaneously, a blur of possibilities only collapsing into one outcome when measured. The many worlds interpretation takes this further, proposing that every quantum decision point doesn't collapse but splits reality itself. When you flip a coin, for instance, both outcomes happen. You just experience one while another version of you lives the alternative. It's as if reality is a tree with infinite branches, each twig representing a universe where history plays out slightly differently. Meanwhile, cosmic inflation, the theory that the early universe expanded exponentially faster than light, implies our universe might be one bubble in a frothy multiverse. As space-time stretched, some regions stopped inflating, becoming stable universes with their own laws of physics, while others kept expanding. The result: a cosmic archipelago where universes with different constants, stronger gravity, weaker electromagnetism, float like islands in a higher dimensional sea. Some might harbor life, others could be sterile wastelands. Here's where it gets tantalizing. These parallel realities might not be so different after all. Quantum branches and inflationary bubbles could be two sides of the same coin, one describing multiplicity from the bottom-up quantum events, the other from the top-down cosmic structure. Imagine the multiverse as a vast quantum computer where every possible state isn't just calculated but physically realized. In this view, cosmic inflation isn't just creating space, it's executing every possible program the laws of physics allow. The implications are dizzying. If true, there's a universe where dinosaurs never went extinct, another where you took that job offer last year, and countless others with alien physics we can't begin to fathom. Some theorists even speculate that quantum entanglement, those spooky links between particles, could be threads tying parallel realities together, with each entangled pair a tiny wormhole bridging worlds. Yet skepticism remains. Without observable evidence, the multiverse risks being untestable, more philosophy than science. But new tools are emerging. Quantum computers manipulating superpositions might one day hint at how branching happens. Telescopes hunting for gravitational wave imprints in the cosmic microwave background could find bruises from collisions with other bubble universes. And if we ever detect anomalies in fundamental constants, pockets of space where physics seems subtly off, it might signal we're near the edge of our cosmic bubble, brushing against another. Whether these ideas converge or not, they push us to rethink reality's nature. The universe might not just be stranger than we imagine, it could be stranger than we can imagine, a fractal of possibilities where every what if plays out somewhere, from the quantum flutter of an atom to the birth of entire cosmoses. The multiverse isn't just a theory about other worlds, it's a mirror forcing us to ask, in an infinity of possibilities, what makes this one special? At first glance, empty space seems like nothingness, a featureless void between stars and atoms. But peer closer, and you'll find a seething quantum ocean where particles flicker in and out of existence like bubbles in a boiling pot. This isn't poetic metaphor, it's a fundamental property of reality called vacuum energy. Every cubic centimeter of so-called empty space crackles with these fleeting fluctuations, where particle-antiparticle pairs borrow energy from the vacuum itself, only to annihilate and repay the debt moments later. It's a cosmic game of hide and seek happening trillions of times per second, even in the darkest reaches between galaxies. The shock comes when you calculate how much energy this quantum froth should contain. According to quantum field theory, the vacuum ought to be unimaginably dense with energy enough to curve spacetime so violently that galaxies couldn't form, and reality would tear itself apart. Yet our universe is curiously flat, its expansion accelerating gently as if guided by an invisible hand. This discrepancy, known as the cosmological constant problem, is one of physics' greatest puzzles. How can vacuum energy be simultaneously enormous in theory and imperceptibly small in practice? The answer might lie in a cosmic balancing act we're only beginning to grasp. Enter dark energy, the mysterious force driving the universe's accelerated expansion. When astronomers discovered in the late 1990s that galaxies were flying apart faster over time, not slower as gravity predicted, they realized something was pushing space itself outward. The leading suspect, vacuum energy's gentler cousin, a uniform, persistent pressure embedded in spacetime. Unlike the violent quantum fluctuations, this energy appears smooth and unchanging, as if the universe's emptiness has a built-in anti-gravity effect. But here's the twist. While dark energy's behavior matches vacuum energy's predicted repulsive push, its measured strength is a staggering 120 orders of magnitude weaker than quantum theory suggests. It's like expecting a hurricane and feeling only a breath. So where does the mismatch come from? Some theorists propose that vacuum energy's chaotic fluctuations might cancel out statistically, leaving behind a faint residual, the dark energy we observe. Others suggest new physics, like extra dimensions or evolving fields, could dilute vacuum energy's potency over cosmic time. There's even the audacious idea that our universe is just one bubble in a multiverse, where most bubbles collapse instantly due to excessive vacuum energy, and we simply inhabit a rare, survivable outlier. Whatever the explanation, the stakes couldn't be higher. Vacuum energy doesn't just shape the universe's fate, it might hold the key to why life is possible at all. The most tantalizing experiments aim to catch vacuum energy in the act. Ultra-precise atomic clocks monitor tiny shifts in energy levels that could reveal fluctuations in the vacuum structure. Meanwhile, tabletop experiments with Casimir plates' metal surfaces placed micrometers apart measure the subtle force created when quantum fluctuations are squeezed out of the gap between them. Even gravitational wave detectors, by listening for space-time ripples at ever higher sensitivities, might pick up whispers of vacuum energy's influence on cosmic scales. From the quantum foam beneath our feet to the accelerating edge of the observable universe, vacuum energy ties the smallest scales to the largest. It's a reminder that nothingness is anything but empty, a dynamic stage where the universe's deepest mysteries play out in the silence between particles and the vastness between stars. Whether it's the hidden engine of cosmic expansion or a clue to realities beyond our own, one thing's certain: the vacuum is alive with possibility. Black holes aren't just cosmic vacuum cleaners, they are also the universe's most enigmatic librarians, guarding secrets in a language we're only beginning to decode. In the 1970s, physicist Jacob Bekenstein made a startling claim: black holes have entropy, a measure of hidden information. This idea was so radical that even Stephen Hawking initially dismissed it, but the math was undeniable. Just as atoms store data in their quantum states, spin, charge, energy levels, black holes somehow encode information about everything they swallow, from stars to stray photons. The twist: this information isn't stored like books on a shelf. It's smeared across the black hole's event horizon in bits so tiny they make atoms look like planets. Picture a black hole's surface as a mosaic of Planck-sized tiles, each one a binary switch holding a single unit of information. The more massive the black hole, the more tiles it has, and the higher its entropy. This mirrors how a gas's entropy increases as its molecules spread into more possible configurations. But here's the cosmic irony: while gas molecules reveal their secrets when you probe them, a black hole's information stays locked away, compressed into a singularity where space-time itself breaks down. Hawking later showed that black holes slowly evaporate, radiating energy, now called Hawking radiation, which posed a nightmare scenario. If the hole vanishes, does the information it swallowed vanish too? That would violate quantum mechanics' sacred law that information can never be destroyed. The resolution came from an unexpected place: holography. Just as a 3D image can be encoded on a 2D surface, a black hole's interior information might be fully stored on its 2D event horizon. When matter falls in, it doesn't vanish, it leaves a shadow on the horizon, a scrambled but preserved record. This idea reshaped physics, suggesting that space-time itself could be a projection of information stored on distant boundaries. The same principles might apply to the entire universe, meaning the 3D reality we experience could be a hologram rendered from data at the cosmic edge. What makes this more than theoretical poetry is the math. Black hole entropy formulas resemble equations from information theory, the science of data transmission and storage. Claude Shannon's work on communication, how much information a phone line can carry, for instance, uses logarithms and probabilities that eerily match Bekenstein's entropy calculations. It's as if the universe runs on a vast, invisible internet with black holes as its most secure servers. The implications ripple outward. If information is a fundamental currency alongside space, time, and matter, then black holes aren't anomalies, they're Rosetta Stones. Their event horizons might teach us how quantum mechanics and gravity intertwine, a puzzle at the heart of modern physics. Already, labs are simulating black hole dynamics with quantum circuits, testing how information behaves at the edge of oblivion. And if holography holds, the very nature of reality might be up for reinterpretation, not as a collection of objects, but as a network of relationships, a cosmic conversation where every bit matters. From the spin of an electron to the roar of a galactic core, information seems to be the thread stitching reality together. Black holes, those darkest of cosmic vaults, might just hold the brightest keys to understanding it all. The constants of our universe seem suspiciously well suited for life, as if the cosmos were meticulously calibrated just for us. Take gravity. If it were slightly stronger, stars would burn out too quickly, slightly weaker, and they'd never ignite at all. The same goes for the strength of electromagnetism, the mass of protons, even the density of dark energy. Tweak any of these values by a fraction, and atoms wouldn't bond, galaxies wouldn't form, and life as we know it would be impossible. This eerie precision is called fine-tuning, and it's one of the most tantalizing puzzles in science. Is it sheer luck, or does our existence hint at something deeper? A cosmic connection between observers and the universe itself. Consider carbon, the backbone of life. For it to form in stars, a rare and precise resonance must exist between the energy levels of helium and beryllium nuclei during stellar fusion. Without this exact match, this atomic sweet spot carbon would be vanishingly rare, and biochemistry might never arise. Even the cosmological constant, which governs the expansion of space, is fine-tuned to 1 part in 10 to the power of 120. That's like balancing a pencil on its tip for billions of years without it falling. The odds seem so absurdly low that some physicists argue it's easier to imagine an infinite array of universes, each with random constants, and we just happen to occupy the one where the numbers lined up right. This is where the Anthropic Principle enters the conversation. In its simplest form, it states that the universe must be compatible with conscious life because, well, we're here to observe it. It's not that the cosmos was designed for us, but rather that we're the inevitable product of its particular rules. Think of it like a puddle marveling at how perfectly its hole fits its shape. But there's a more provocative version, the participatory anthropic principle, which suggests observers might play an active role in shaping reality. Quantum mechanics already shows that particles exist in probability clouds until measured, so could consciousness itself be a thread woven into the fabric of the universe? Critics dismiss fine-tuning as a selection bias. We can only ponder these questions in a universe that allows our existence, yet the precision is hard to ignore. Even the ratio of electrons to protons is exquisitely balanced. A tiny difference would prevent stable atoms from forming. Some theorists propose wilder explanations, like the universe being a simulation with optimized parameters, or a self-replicating entity where life is a feature, not a bug. Others see fine-tuning as evidence of a deeper, undiscovered physics, a theory where these constants aren't arbitrary, but emerge naturally from underlying principles we haven't yet uncovered. The search for answers is driving cutting-edge science. Particle colliders hunt for clues in the behavior of exotic particles, while astronomers map the cosmic microwave background for anomalies that might reveal hidden dimensions or alternate universes. Meanwhile, philosophers grapple with the implications. If the universe truly is fine-tuned, does that demand an explanation beyond brute chance? Whether through multiverses, new physics, or something even stranger, the Anthropic Principle forces us to confront a humbling possibility, that we're not just bystanders in the cosmos, but participants in its grand, mysterious story. The act of observing a quantum particle seems to reach beyond the microscope somehow. The very act of measurement forces a fuzzy cloud of possibilities to snap into a single, concrete reality. This phenomenon, called the observer effect, lies at the heart of one of quantum mechanics' most contentious debates. Does consciousness itself play a role in shaping reality? The idea traces back to the pioneers of quantum theory. When Niels Bohr and Werner Heisenberg argued that particles exist in superpositions until measured, they weren't just talking about lab equipment, they hinted that the observer's mind might be part of the equation. Decades later, physicist John von Neumann took it further, suggesting that the collapse of quantum probabilities isn't complete until it enters a conscious observer's awareness. It's as if the universe hesitates, holding its breath until someone or something looks. But what if this quantum quirk isn't confined to lab experiments? Could consciousness, on some level, influence the cosmos itself? Consider galaxy formation. The distribution of matter in the universe follows patterns that emerged from quantum fluctuations during cosmic inflation. If consciousness can collapse quantum states, might it also nudge those primordial seeds, subtly steering where galaxies cluster? It's a wild idea, but not without precedent. In the lab, the quantum Zeno effect shows that frequent observation can freeze a system's evolution like a watched pot that never boils. Scale this up, and one could speculate that universal structures might freeze into place under some form of cosmic observation. Critics, of course, dismiss this as mysticism dressed in scientific jargon. They argue that observation in quantum mechanics simply means interaction with any macroscopic system, a photon hitting a detector, not a mind pondering the result. Yet intriguing experiments linger at the edge of this debate. Delayed choice experiments, where a decision to measure a quantum system is made after the particle's choice should already be set, suggest that time itself might not be as linear as we think. Some interpretations propose that consciousness could be retroactively influencing the past, weaving causality into knots that defy classical logic. The implications spiral outward. If consciousness and quantum mechanics are entangled, then the universe might not be a static stage but an interactive canvas. ancient philosophies like idealism, the notion that reality is fundamentally mental, suddenly find themselves in dialogue with cutting-edge physics. Even artificial intelligence enters the fray. If a sophisticated AI observes a quantum system, does it count as a conscious observer? The boundaries blur between mind, matter, and the fabric of space-time. Whether consciousness is a passive witness or an active participant remains unresolved, but the question itself reshapes how we see our place in the cosmos. From the flutter of an electron to the swirl of a galaxy, reality might not just be something we observe, it could be something we, in part, create. The universe, in this light, isn't a finished painting but an ongoing collaboration between the seen and the seer. A shattered glass never reassembles itself, a campfire's heat never flows back into the logs, and the universe never rewinds, all because of a relentless cosmic rule called entropy. This isn't just about disorder, it's the hidden force that gives time its arrow, its one-way direction from past to future. At the atomic level, entropy is a numbers game. Imagine a box of red and blue marbles, shake it, and they'll mix into a jumble. The odds of them spontaneously separating again are astronomically low, not because it's impossible, but because there are vastly more mixed states than ordered ones. That's entropy in action, nature's preference for spreading energy and matter into as many configurations as possible. Now zoom out to the cosmic scale. Stars burn their fuel, converting ordered nuclear energy into scattered starlight. Galaxies collide, transforming neat spiral arms into chaotic tidal streams. Even black holes, those perfect traps of gravity, aren't immune. They slowly evaporate via Hawking radiation, their immense order dissolving into faint heat. The universe started in a state of unimaginable low entropy right after the Big Bang, a hot, dense soup with energy packed neatly together. Ever since, it's been climbing toward higher entropy, like a ball rolling down an endless hill. But here's the twist: entropy isn't just a passive trend. It might be the reason time feels like it flows at all. At the quantum level, particles don't care about past or future. Their equations work equally well in reverse. Yet when trillions of particles interact, their collective dance follows entropy's lead, creating the illusion of time's arrow. Think of a movie reel. Each frame is timeless, but play them in sequence, and suddenly there's a story. The universe might work the same way, with entropy stitching together microscopic moments into the relentless march of time we experience. This raises a haunting question: why was entropy so low at the beginning? Some theorists suggest our Big Bang wasn't the true starting point but a rebound from a previous universe's collapse, a cosmic reset that briefly lowered entropy. Others propose a multiverse where countless universes spawn with random initial conditions, and we simply inhabit one where the numbers lined up right for complexity and life to emerge. Whatever the answer, entropy binds the fate of quarks to quasars, proving that time's flow isn't just a human perception but a fundamental thread woven through every scale of existence. String theory dares to rewrite the cosmic rulebook by suggesting that everything from the quarks in your atoms to the black holes swallowing galaxies is woven from the same fundamental ingredient: tiny, vibrating strings. Unlike the point-like particles of traditional physics, these strings are one-dimensional filaments, each vibrating at distinct frequencies like guitar strings playing different notes. The pitch of their vibration determines whether they manifest as an electron, a photon, or even a graviton, the hypothetical particle carrying gravity's force. This elegant idea promises to solve one of physics' greatest puzzles: why gravity, which sculpts the cosmos on grand scales, resists integration with the quantum laws governing the subatomic world. Imagine plucking a violin string. The same string can produce multiple notes depending on how it vibrates. Now shrink that string to a billionth of the size of a proton, and you've got the essence of string theory. It's a vision where the universe's diversity emerges not from a zoo of unrelated particles, but from harmonies played on microscopic strings. Even better, this framework naturally includes gravity. While general relativity describes gravity as the curvature of spacetime, string theory recasts it as the exchange of gravitons, closed-loop strings vibrating just right to transmit the gravitational force. Suddenly, the quantum and cosmic scales aren't at war. They're different verses of the same vibrational symphony, but there's a catch, or rather, 10 of them. String theory only works if the universe has extra dimensions beyond the 4 we experience. These hidden dimensions could be curled up so tightly that even atoms seem vast by comparison, like a garden hose appearing one-dimensional from a distance but revealing its cylindrical shape up close. Some models propose these dimensions are Calabi-Yau manifolds, intricate 6-dimensional shapes that dictate how strings twist and vibrate. The math is beautiful, but the implications are dizzying. The properties of every particle, every force, might depend on the geometry of dimensions we can't see. Critics argue string theory's lack of experimental proof leaves it in limbo. Unlike quantum mechanics, which predicted antimatter, or general relativity, which foresaw black holes, string theory's energy scales are trillions of times beyond what particle colliders can probe. Yet indirect clues tantalize. The holographic principle, which suggests our 3D universe could be encoded on a 2D surface, emerged from string theory math. Black hole entropy calculations, once paradoxical, now align neatly with string-theoretic models. Even the search for supersymmetry, a predicted symmetry between particles that string theory requires, has driven decades of research at facilities like the Large Hadron Collider. Perhaps the most profound insight string theory offers isn't about strings at all, but about unity. It paints reality as a vast, interconnected web where the laws governing galaxies and atoms aren't just similar. They're literally the same phenomena observed from different perspectives. From the quantum flutter of a string to the gravitational dance of galaxies, the universe might be playing a single, endless song, composed in dimensions beyond our sight but resonant through every scale of existence. Whether string theory ultimately holds or not, its bold vision challenges us to listen deeper, to hear the hidden harmonies that could bind all of reality together. From quantum entanglement to galactic superclusters, these 30 cosmic threads reveal a universe far more interconnected than we ever imagined. Each discovery peels back another layer, showing how the micro and macrocosmos dance to the same hidden rhythms. Whether it's the eerie symmetry between atomic nuclei and neutron stars, the way dark matter's invisible scaffolding mirrors the quantum bonds holding atoms together, or the fractal patterns repeating from your neurons to the cosmic web, the universe seems obsessed with recycling its most elegant blueprints. Think about what this means for our place in the cosmos. The calcium in your bones was forged in the hearts of dying stars, while the quantum fluctuations that birthed galaxies also dictated the neural pathways firing as you read these words. You're not just a bystander to the universe's grand story. You're a living, breathing chapter written in stardust and shaped by forces older than time itself. The same laws that guide electrons around an atom's nucleus also choreograph the whirl of planets and the spin of galaxies. Scale, it seems, is just an illusion, a trick of perspective hiding the deeper unity beneath. This isn't just poetic musing, it's a revolution in how we understand reality. For centuries, science carved the universe into separate domains: biology here, physics there, astronomy over yonder. But the boundaries are blurring. Quantum biologists explore how entanglement might play a role in photosynthesis, while cosmologists borrow equations from fluid dynamics to model the birth of galaxies. The toolbox of discovery is becoming universal, proving that the threads connecting the smallest particles to the largest structures aren't just metaphorical, they're mathematical, measurable, and breathtakingly real. As we stand on the precipice of new breakthroughs, from next-generation particle colliders to telescopes peering back at the universe's first light, one truth becomes clear: every answer uncovers deeper questions. What if dark matter is a shadow of undiscovered particles at the quantum scale? Could the universe's expansion be tied to vacuum fluctuations we've yet to detect? The more we learn, the more the cosmos humbles us with its layered complexity. So here's the invitation: keep looking up and keep looking inward. The atoms in your hand and the stars above are part of the same grand tapestry, woven from forces both ancient and ever new. Share your thoughts in the comments. What cosmic connection fascinates you most? And if you've enjoyed this journey through the universe's hidden threads, don't forget to subscribe. The cosmos has countless more mysteries waiting, and we're just getting started.